Good morning. Next, we are going to see the third unit, that is design of sequential circuit, synchronous sequential circuit. So first, we are going to see the topic in unit 3, that is design of synchronous sequential circuits. Okay. Now, before going into the design, you must know some definitions. First, what is meant by state? The information stored in the memory elements at a given time defines a state. Memory elements mean either flip-flop or latch. The information stored in the memory elements at the given time defines the state. Now, present state. The status of all state variables at some time t before the next clock edge represents the present state. Or in other words, you can say the present state is nothing but it is a state of the flip-flop before the application of input and clock. It is nothing called present state. Next state. The status of all variables at the time t plus 1 after the next clock edge represents the present state. So next state is nothing but it is a output of the flip-flop after the application of clock and input. It is nothing called next state. Okay. Now next one, state table. So state table is a table which gives a relationship between present state, input, next state and output. So state table gives the relationship between present state, input, next state and output. Then state diagram. State diagram is a pictorial representation of behavior of sequential circuit. So from the diagram we can understand the behavior of a sequential circuit. In state diagram, state is represented by circle. In state diagram, state is represented by a circle and the transition between the states for different input conditions and the outputs are indicated by direct lines connecting the circle. So the state diagram is nothing but the pictorial representation of behavior of the sequential circuit. Or in other words, we can say state diagram is a pictorial representation of state table. Okay, it will give us idea about the present state, input, next state and output. Okay. And in state diagram, state is represented by a circle and the transition between the states for different input conditions and outputs are indicated by direct lines connecting the circle. Okay. First, we are going to study the steps for the design of clocked or synchronous sequential circuit. The synchronous sequential circuit is also called as this clocked sequential circuit or finite state machines. So these are the other names for this synchronous sequential circuit. It is also called as finite state machines or clocked sequential circuit or synchronous sequential circuit. Now we are going to study what are the steps for the design of synchronous sequential circuit. First step is it is necessary to first obtain the state table from the given information. So from the given information such as state diagram or timing diagram or any other pertinent information, we have to get the state table. First table is obtaining the state table from the given information. Second step, the number of state may be reduced by state reduction technique if equivalent states are present. So from the state table, if equivalent states are there, we have to go for state reduction. Two states are said to be equivalent if they have same input and if they are having same next state and same output. So what is equivalent states? Two states are said to be equivalent if they are have same next state and same output, then they are called equivalent states. So if there are equivalent states, then you have to go for state reduction. So we have to reduce the number of states. So third step is we have to assign binary values to the each state. So you have to give binary values to each state in the state table. Next is determine the number of flip-flops needed and assign letter symbols to each. So next step is we have to determine the number of flip-flop needed to implement, and we have to assign letter symbols to the flip-flops inputs. Then We have to choose which type of flip-flop we have to use for the particular design. Then from the state table, derive the circuit excitation and output tables. Then using K-map, the circuit output function and flip-flop input function. So using K-map, we have to derive the circuit output function and flip-flop input function. So next we have to draw the logic diagram from the Boolean expression what you get by reducing the K-map. Next is we have to draw the logic diagram. So next we are going to see a problem. Design a clocked sequential circuit for the state diagram shown in the figure. So this diagram is called a state diagram. So state diagram is nothing but it is a pictorial representation which gives the behavior of a, a sequential circuit or clocked sequential circuit. Or in other words, the state diagram is nothing but a pictorial representation of state table. It gives relation between the present state input, next state and the output. So what we have to do means they have given the state diagram. From this state diagram, we have to form the state table. That is the first step of the design. So I will explain here. This is a state diagram. Here states are represented by circles. So how many states you are having? A, B, C, D, E, F, G. Okay. So you are having states from A to D. You are having 7 states A, B, C, D, E, F, G. Now this is state A, this is state B, this is state D, this is state C, this is D, E, F, and G. Now the transition between the states it is represented by line segment with arrowheads. Now here you are having the values. The first value before the slash it indicates the input, and the second value indicates the output. So this is nothing but input, and the 0 is nothing but the output. So this is state diagram. So from this state diagram we have to draw the state table. Now we are considering the state A. When we are giving the input 0, it is going to the output, it is going to the state C. So you are in state A. When you are giving the input, you are in state A, you are giving the input to 0, and it is going to state C, and the output is 0. Similarly, you are in state A. When you are providing the input to 1, it is going to state B, and the output is 0. Okay, we have written the possibilities for A. A is having two inputs, one is 0 and another is 1. And when giving 0, it is going to C, and when you are giving 1, it is going to B. And the outputs are 0. Next, we are coming to state B. When you are giving the input as 0, it is going to D. It is going to D. When you are giving the input to 0, it is going to D, and the output is 0. You are in B. When you are giving the input 1, it is going to C, and the output is 0. Similarly, you are in C. When you are providing input 0, it is going to G, and the output is 1. Similarly, you are in C. When you are providing the input 1, it is going to D, and the output is 1. You are in D. When you are providing the input 0, it is going to E, and the output is 1. You are in D. When you are providing the input 1, it is going to F, and the output is 0. You are in state E. When you are providing the input 0, it is going to F and the output is 0. You are in E, when you are providing the input 1, it is going to A and the output is 1. You are in F, when you are providing input 0, it is going to G and the output is 0. So next we are in state G, when you are providing the input 0, it is coming to F, output is 1. You are in G, when you are providing the input 1, it is going to A, output is 1. So you are in state F, when you are providing the input 1, it is going to 0. So these conditions or these details are present in this state diagram. So from this state diagram, we are going for the state table. So this is the state table. The state table will be having the information about the present state, next state, and output. So here there are two inputs, that is one is x is equal to 0 and another one is x is equal to 1. Here we have taken the input as x. Similarly, here there are two conditions, when x is equal to 0 and x is equal to 1. So these are the present states. So we are having the states from A to, so here we are having states from A to G. So we are having states from A to G, and this state table is having the information of present state, next state, and output. Now I will tell how to write the first row. Similarly, you have to write the second, third, fourth, and fifth. So first condition is we are taking present state as A. We are taking the present state as A, and when you are providing x is equal to 0, when you are providing input x is equal to 0, it is going to the next state C, and in output, this is output, x is equal to 0 and x is equal to 1. The output you have to put 0. Similarly, when you are providing x is equal to 1, you are in state A, when you are providing x is equal to 1, it is going to B, output is 0. Similarly, next one, you are in state B. We are in state B, when you are providing input is equal to 0. When you are providing input is equal to 0, it is going to D. Similarly, output is 0. You are in state B, when you are providing the input as 1, it is going to C, and the output is 0. Similarly, you take C. You are in state C, when you are providing the input as 0, it is going to G, and the output is 1. And you are in state C, when you are providing the input as 1, it is going to D, and the output is 1. Similarly, you are in state D, when you are giving input to 0, it is going to E, and output is 1. You are in D, when you are providing input 1, it is going to F, and output is 0. Then you are in F, you are in F, when you are providing input 0, it is going to G, output is 1. When you are providing, so you are in F, when you are providing input is equal to 0, it is okay. You are in F, when you are providing input 1, it is in the same F, and the output is 0. You are in G, when you are giving an input of 0, it is going to F, output is 1. And when you are providing 1, it is going to A, and output is 1. So this is nothing but the method to write the state table. So this values we have to enter in the next table, that is state table. From this state diagram, we have to find the state table. So by looking this state diagram, we have to, once again I will tell how to write the state table. So I am taking present state as A. From this state diagram, when I am providing the input as 0, it is going to C. This is the input 0, it is going to C. So when input is 0, the output is 0. So in the place of output, I am putting 0. When A is 1, I am giving the input as 1, it is going to B. So I am writing as B. And the output here is 0. I am writing as 0. Similarly, I have to take B and I have to write the so in state B, when I am providing input to 0, it is going to D and the output is 0. Similarly, when I am in B, when I am providing the input 1, going to C and the output is 0. Similarly, I have to write it for C, D and E. Okay. So now we have formed the state table from the state diagram. So we have formed the state table from the state diagram. Now next step is we have to check for equivalent states. So equivalent state is nothing but next step is checking for equivalent state. Two states are said to be equivalent if they have the same next state and same output. So first I am checking A and B. It is not having same. Here the next state is C, here the next state is D. So we can't check A and C. Here it is G, no chance. You check A and D, you compare. Here C, here E, no chance. Then A and E, no chance. A and F, no chance. A and G, no chance. Then I am comparing B with C, no chance. D, no chance. E, no chance. F, no chance. G, no chance. Then I am comparing C with D. Here it is different. So then E, it is different. Then C and F. Here you are having G. 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 No problem. But here you are having D and here you are having F. So it is not equivalent. So if equivalent state means both the next state will be same and both the output is same. Here also the output is different. Here you are having 1 and here you are having 0. So C and F are not equivalent. So we have to go for the C and F. Okay. Next we are going for C and G. C and G. So here F, G, you have no chance. Now you are going for D. Compare D with E. Not possible. D with F. Not possible. D with G. Not possible. Now I am going to compare E with F. It is not possible. Then I am comparing E and G. Here you are having F. Here you are having F. Here you are having A. Here you are having A. Here you are having 0, here you are having 0, here you are having 1 and here you are having 1. So E and G are equivalent. Why? Because they are having the same next state. They are having the same next state and same output. Since E and G are having same next state and same E and G are having same next state and same output. So E and G are equivalent state. So you can reduce one state. Instead of E and G, we can take only E. So I will explain it in the next step. So checking for the equivalent state is a next step. Here states E and G are equivalent. Since G and E are having same next state and same output. So we have to replace G by E. So we have to replace G by E. So in the table we have replaced G by E. Instead of G we have put it as E. So we are having 2 E. So we are needed to take only one. One E is enough and we can reduce one state. So we'll be having A, B, C, D, E and F. So from 7 state we are reduced to 1, 2, 3, 4, 5, 6 states. We are reduced to 6 states. Next is again we are checking for equivalent states. Again we are checking for equivalent states. So you neglect this E state. Similarly, wherever you are having G, we have to cut it and you have to put it as E. So wherever in whichever places you are having G, you have to cut it and make it as E. Now again we are checking for equivalent states. So I am comparing A and B, no chance. A and C, no chance. A and E, A and D, no chance. A and E are A, C, no chance. D, no chance. No, no chance. But B, I am comparing B with C, no chance. C, D, no chance. I am comparing C with D, no chance. C with E, C with I am comparing D D with F. I am comparing D with F. So it is having the same next state. I am comparing D with F. They are having same next state. Here you are having EF. Here also you are having EF. I am then comparing the output. They are having same output. So the states D and F are having same next state and same output. So states D and F are equivalent. So wherever you are having F, you can cut it and you can write it as D. Wherever you are having F, you can cut it and you can write it as you can F you can cut it and you can write it as D. Wherever you are having F, you cut it and you write it as D. So again from the previous table, D and F are equivalent. So we have same output since it is having same output and same next state. So we have replaced the F by D. So here initially we have replaced F by this is actually F. We have replaced it by E. Then sorry G we have replaced it by E and F we have replaced it by D. Now you are having two D's and two E's. So instead of two D's you have to take only one and instead of two E's you have to take only one. So we have reduced the state table to initially it is having 7 rows. Now we have reduced it to 5 rows. So we have initially from the state diagram we have formed the state table. From the state table we have checked for equivalent state. Equivalent state means two states having same next state and same output. So after that we have reduced again we have checked for equivalent states. Again we got one two states equivalent. Again we have reduced. So from 7 state we have reduced to 5 states. Again we are checking whether there is any possibility of equivalent states. Here C, any other? No. Here D, any other state is having D? No. Here you are having E. Here you are having E. Here you are having D. C and D are having same next state, but their outputs are different. Here it is 1 1 and here it is 1 0. So they are not equivalent. So equivalent means same next state as well as same output. So we have reduced the 7 states to 5 states. So this is the reduced state table. So next, from the reduced state table, we are going to state assignment. State assignment means assigning binary values to the states. So here you are having 5 states. So in order to represent 5, minimum we need 3 bits. So we are going to represent each state by 3 bits. So we are representing each states by 3 bits. I am taking from 001 for A, 010 for B, 011 for C, 110 for D, and 100 for D, and 110 for E. So I have, this is the step 4 is state assignment. State assignments mean assigning binary values to the states. Now I am converting that reduced state table to transition table. So reduced we are converting the reduced table to transition table, and we are designing this circuit by using D flip-flop. So this is a transition table. So how we are getting the transition table means, now from the transitions table we have from the uh, reduced table we are coming for the transition table. So in transition table the states are having the value A is equal to 0 0 1. I will tell for the first one. So I am taking A is equal to 0 0 1. So I am giving the input 0. So from the state table, so from the state table we know that when A the value of A what you have taken after state assignment is 0 0 0, and when x is equal to 0 it is going to C. The value of C is 0 1 1. Similarly when you are in state A, that is 0 0 0, when you are providing x is equal to 1 it is going to B, that is 0 1 0. So you are converting this state table into transition table. You are just assigning value. For the next one, we are taking 0 0 1 for B. So when you are providing x is equal to 0, it is going to D. D means 1 0 0. When you are providing x is equal to 1, it is going to C. C is nothing but 0 1 1. So you are converting like this. Instead of states, you are putting the values. So uh, this is the transition table. Instead of state A, we have taken 0 0 0. Since it is 3 bits, we have used capital A, capital B, and capital C. For input, we have taken as X. For the next state, we have taken as the from when you are giving A is equal to 0, A is 0 0 0. When you are giving the input 0, it is going to C. The value of 0 C is 0 1 1. Similarly, we are taking A. A is 0 0 1. When you are providing x is equal to 1, it is going to B. The value of B is 0 1 0. Okay. So at the time when x is equal to 0, the output is 0. Similarly, at x is equal to 1, the output is 1. We have to fill that output also. For the next one, we are taking B. B value is 0 1 0. When you are having 0 1 0, when you are providing x is equal to 0, it is going to D. D value is 1 0 0. At that time, the output is 0. Similarly, when you are providing the input, when you are in state B, that is 0 1 0, and when you are providing the input 1, it is going to C, that is 0 1 1, and the output is 0. Similarly, you have to write it for C, D, and E. This is nothing but transition table. Transition table is nothing but just converting your state table into by assigning the value, binary values to the state table, and just you are modifying the state table. That is nothing but transition table. In state table, so after converting this state table into transition table, then we have to find the number of flip-flop which is needed to implement this circuit. Okay, so the conversion of state table is to transition table is just assigning binary value to the states. Then instead of alphabets, we have to use the binary values. Okay, that is the conversion of state table into transition table. So after completing this transition table, then we are to find the number of flip-flops needed. Okay, so the number of flip-flop needed. So for one variable, you need one flip-flop. So for B, DB, for C, DC. Please listen. Here we are doing it by D flip-flop. Unless mentioned in some problems, they will clearly mention do it by SR flip-flop or do it by JK flip-flop. If they are mentioning do it by a particular flip-flop. If not mentioned, you go for D or T, because if you go for D and T, these flip-flops are having only one input, and the number of K-maps you have to solve with will be lesser than when you are comparing to JK and SR. So it is better to go for T or D when it is not mentioned in the question. Do it by particular flip-flop. So here we have choose the D flip-flop for doing this problem. By doing this problem, we have choose the D flip-flop. The next state equation of D flip-flop is nothing but Q of n plus 1 is equal to D. So dA is nothing but A1. If we just copy this A1 to dA, then you will be getting dA. When you copy B1 to dB, you will be getting dB. When you copy C1 to DC, you will be getting DC. So this is the simplest thing. Doing by D flip-flop is more simple. Okay. So I am doing this problem by D flip-flop just to copy A1 to dA, B1 to dB, and C1 to DC. Okay. So you will be getting the transition table like this. So you'll be getting the full transition table. This transition table is having present state, it is having input, it is having next state, and it is having flip-flop input. It is having flip-flop input and it is having output. Now we have to implement the circuit. So in to implement the circuit, we have to implement by using flip-flop. You have to implement it. So we have to find the input DA, expression for input DA, in expression for input DB, and expression for input DC. Similarly, the output Y we have to find. Now in this problem, the inputs are A, B, C, and X. You forget about the next state. You have to consider the present state and input. So when you are considering this present state and input, totally you will be getting four variables, that is A, B, C, and X. So the output is nothing but you are going you have to draw K maps for DA, DB, DC, and Y. So you have to draw four variable K maps. Then how to get the value of dA means K map for dA is nothing but you have to check the column of dA wherever you are having one for that particular input. That is nothing but this is the input for this one, that is 0 1 1 0. For 0 1 1 0 in the K map you have to put 1. Similarly, next one for 0 1 1 1 in the K map you have to put 1. Similarly, 1 0 0 0 you have to put 1 in the K map. Similarly, 1 0 0 1 you have to put 1 in the K map. Similarly, 1 1 0 0 you have to put 1 in the K map. So please listen, another important thing is, so in this problem how many input variables you are having? You are having 4 input variables. So if you are having 4 input variable, you must have 16 combination. That is from 0 to 15 combination you must have. But here you are not having 16 combination. Then now you check which are the numbers missing. This is 2. 0 0 1 0 is 2. 0 0 1 1 is 3. This is 4. This is 5. Then this is 6, 7, 8, 9, 10 and 11. 10 and 11. So please listen. Here 0, 1. Then um, 0, 11. Then uh, 0 is missing. Here 0 is missing. 1 is missing. Then 10 is missing. 11 is missing. 12, 13 is there. 14 is missing. 15 is missing. For this missing numbers, these missing numbers are the unused states here. So in the K map, you have to put don't care in the unused states. Clearly, I will tell now. So here we are doing it by using D flip flop. So next state equation, next state is equal to D input. So DA equal to A1, DB equal to B1, DC is equal to B1. So we are going for the problem. So this is a K map for DA. So in that some of the states are don't care unused state, that is 0, 1, 14, 15, 10, 11. These are the unused states. In these unused states, you put don't cares. Then you check the column of DA, and wherever you are having 1, you plot once in the K map of DA. Okay. Then you go for grouping. So here you are having 1 octet and 1 quad. So the expression is nothing but for this one it is A, for this one it is B x bar. So this is the expression is dA is equal to A plus BC plus BX bar. So here while grouping you will be getting the expression of dA is equal to A plus BC plus BX. Now we are going for the K map of DB. Okay, so you will be checking the column of DB. Wherever you are having 1, you will be plotting. Then you will be putting down case in the place of unused states, and you are grouping. So you are having 1, 2, 3, 4 quads and 1 pair. So this is the expression you will be getting A bar C bar plus B bar C plus B bar X bar plus C X bar. This is the expression you will be getting. Next DC, expression for DC. These are the two group you will be getting, and this is the expression. Now it is for output Y. We are looking the column of Y. Wherever you are having 1, you have to plot. Then you have to put the down case in the place of unused state. Then you have to group. The expression is Y is equal to A B bar X bar plus BC plus AB X. Now we have to go for implementation. Here we have used 3 D flip flop. So first we are drawing 3 D flip flops, DA, DB and DC. Then the output of DA is A, and its complement output is A bar. Similarly, the output of DB is B and B bar, and C is C and C bar. Now you should give clock to the 3 flip flops, and you have to implement the expressions. So actually, if it is A, you have to take a connection from here and you have to give here. So if it is B, you have to take a connection here and you have to give it to B. Similarly, X bar means here you are having X bar, you have to take a connection and you have to give it to here. Similarly, B means you have to take a connection from B. Similarly, C, so X bar. So you have to connect like this. This is output. So output means you have to take from A, similarly from B, and similarly from X. Similarly, this one you have to give the respective connections and you have to complete the logic diagram. Okay, this is the implementation. So this is the first method. The first step is you from the state diagram you have to form the state table. From the state table you have to go for equivalent state. If there is any equivalent state, then you have to reduce the state table. After reducing the state table, you have to go for state assignment. Then a number of bits depends upon the how much states you are having. So in this problem, you are having 5 states. So the minimum bits required to represent 5 is 3. So use the 3 variables A, B, and C. So and we have used 3 bits to represent each state. So we have used 0, 0, 1 for A and 0, 1, 0 for B, and so on. Now after that, we have converted the state table into transition table. So transition table is nothing but that table consists of binary values instead of the alphabets A, B, and C. From the transition table, we have found out the flip-flop input. Before going that, we must know how many flip-flop needed to implement. So in this problem, since we are having 3 variables, we are need 3 flip-flop, DA, DB, and DC. So unless mentioned, it is better to go for D flip-flop or T flip-flop. In this particular problem, we have used D flip-flop. In the D flip-flop, next state is nothing but Q of n plus 1 is equal to D. If you copy the next state, A1 to DA, B1 to DB, and C1 to DC, will be getting that inputs for DA, DB, and DC. And finally, the output. So here you are having 3 variables, the present state A, B, C, and the input X. And we are going to draw the K-map for DA, DB, DC, and Y. So since we are having 4 variables, we are going for 4 variable map and DA, DB, DC, and Y. Totally 4 variable map. After getting the after checking the individual columns of DA, DB, and DC, we have plotted in the K-map. For the unused states, we have plotted X. Then we have grouped and found out the expression. After getting the expression, we have implemented by using the flip-flop. Next, we are going to see another problem. Design a clocked sequential circuit for the state diagram shown in the figure. They are use JK flip flop. So in this question, they have asked us to do it by using JK flip flops. Use JK flip flop design by using unused states. They are asking again. They are telling us to use the unused states. Okay. Now, so this is a given state diagram. So in the state diagram, when you are in state A, when you are providing the input 0, it is going to state B and having an output of 1. Similarly, when you are in state A, when you are providing the input of 1, it will be going to state C and having an output of 1. Similarly, when you are in state B, when you are providing input 0, it is going to A and having output of 0. Similarly, you are in state B. When you are providing an input of 1, it is in the same state B and the output is 0. Similarly, for C, A, this is a given state diagram. So this is a given state diagram. From this state diagram, we have to form the state table. So totally how many states you are having? 1, 2, 3, 4, 5. We are having 5 states. So we have to write the state table. How we will be writing? In the state table, we will be having present state, then next state x is equal to 0, x is equal to 1, then output x is equal to 0, x is equal to 1. For A when you are providing input 0, it is going to B, output is 1. Similarly, A when you are providing input 1, it is going to C, output is 1. Similarly, when you are in B, when you are providing input, it is going to A, output is 0. When you are providing input 1, it is in the same state B and the output is 1. Similarly, we have to write it for all the states. So this is the state diagram what you will be getting from the state table. So you are having state A, B, C, D and E. So we have got the state table. The step 2 is nothing but we have to check for equivalent state. What is equivalent state? Two states are said to be equivalent if you are having same next state and same output. So now we compare with A with B, A with C, A with D, A with E. No chance. Here you are having B, here you are having A. When you are comparing with A and B, when you are comparing with A and C, you are having B, your D. So your B, here E, here B, here E. No chance for this one. Then similarly, you have to compare with B and C. No chance. B and D, no chance. B and E, no chance. Okay. Now C and D. No chance. Now D and E. So first states are same, but the second is different. So in this problem, there is no equivalent state and state reduction can't be done in this problem. Okay. So next you have to go for transition table. So here totally your state table is having 5 states. So in order to represent 5 in binary, you need minimum three bits. So are representing each state by 3 bits. So I am taking A is equal to 0 0 0, B is equal to 0 1 0, C is equal to 0 1 1, D is equal to 1 0 0, and E is equal to 1 0 1. Okay. Now I am going to convert this state table to transition table. In transition table, instead of alphabets for states, we will be having this binary values. So this is the present state and this is A. Value of A when it is having 0 where it is going. Okay, instead of this, so we'll be getting this uh, this transition table with present state input and output and flip-flop inputs. So here how many variables you are having in the present state? 3 variables. So you need 3 flip-flops. The type of flip-flop what they have mentioned is JK flip-flop. So you have to go for JK flip-flop. Now we'll be converting that state table into transition table. Next, we need to find number of flip flops. So here you are having for A you need one flip flop that is JAKA, and for B you need another flip flop JBKB, and for C you need another flip flop JCKC. So we need 3 flip flop. So next we need the excitation table to fill this JKA, JBKB, JCKC. So we need excitation table to fill this. So first of all, so this is the excitation table of JK flip-flop. If your present state and next states are 0, you have to put 0 in the place of J, and in the place of K you have to put X. So if your present state is 0 and next state is 1, you have to put 1 in the place of J and X in the place of K. If your present state is 1 and next state is 0, you have to put X in the place of J and 1 in the place of K. So if both present state and next state are 1, you have to put X 0. So for 0 0 you have to put 0x. For 0 1 you have to put 1x. For 1 0 you have to put x1, and for 1 1 you have to put x0. Now we are going to fill the inputs for flip-flop inputs. Now we are going to see the present state A and next state A1. So if present state is 0 and next state, so for 0 0 you have to write it as 0x. Similarly, then you have to take the present state B and B1. For 0 1 you have to write it as 1x. Similarly, for 1 0, you would write x1. So this we are getting from the excitation table. Next one, we have to compare a and a1, 0 0. So 0 x, b and v1, 0 1 means 1x. Similarly, 1 1 means x 0. Again, you have to compare a with a1. 0 0 means 0 x. Then 1 0 means x 1. Then 0 1 means 1 x. Similarly, 0 0 means 0 x. Then 1 1 means x 0. Then 0 0 means 0x. So you have to fill this value of j and k like this. So you will be getting the transition table like this. So you'll be getting the transition table like this. In this problem, the input variables are a, b, c, and x. Inputs variables are a, b, c, and x, and you have to draw k maps for the flip-flop inputs JA, KA, JB, KB, JC, and KC. Similarly, for the output to Y. So you have to draw 1, 2, 3, 4, 5, 6, 7. 7 4 variable K map. So in the input, how many variables you are having? We are having 4 variables. So if you are having 4 variables, we must have 16 combinations, 0 to 15. So out of this 15, some of the terms are some of the combinations are missing. That combination is called unused state. So you have to put don't cares in the place of unused states, and then you have to do this problem. This is the excitation table. Then this is a uh, uh, this is a K map for JA, but in this K map we have not included the don't cares. We have just by looking the column of JA, we have just plotted the ones, zeros, and X. Similarly, for KA, we have just plotted X, zeros, and ones. Similarly, for JB, we have included we have entered the 1, 0, and X of particular column. Similarly, for KB, we have entered only the X, 1, and zeros. Similarly, JC and KC. Next, in the remaining places, now what we are doing is, by looking the column, we have entered all the things because we have entered the zeros, ones, and X. So the remaining places are nothing called unused states. So in unused states, we have to put don't cares. So here already we have uh, plotted the zeros, ones, and don't cares from the column of JA. So in that some of the cells are empty. That empty cells are nothing called unused states. In these unused states, we have put don't cares. So this can be done in one step. So I will tell how this can be done in one step. First, we have to go for that truth table. Then we have to find out what are the unused state, and we can directly do it in one step. So instead of doing it in two steps, we can do it in one step. I will tell how. The decimal value of first input is 2. Next one 3. That is 0 0 1 0 is 2. 0 0 1 1 is 3. 0 1 0 0 is 4. Next one 5. Next one 6. Next one 7. Next 8. Next 9. 1000 is 8, 1001 is 9, then 10 and 11. So these numbers, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These numbers are used states, and unused states are actually you have to have numbers from 0 to 15. So here the unused states are 0, 1, 2, 3 are there, 4 there, 5 there, 6 there, 7, 8, 9, 10, 11. Then 12, 13, 14, 15. So if you put don't cares in these numbers in the K map, then you can directly do it in one step. Just you have to check the column of J. Wherever you are having 1, you have to plot. Similarly, wherever you are having don't cares, you have to plot. Then in these numbers, that is 0, 1, 12, 13, 14, 15. In these numbers, you have to put don't cares. Then you can do it in one step. So instead of do it in two steps, you can do it in one step. So first what you have to do, you have to put once in the K map for JA. Then you have to plot X don't cares for the JA. Then you have to plot don't cares in this 0, 1, 12, 13, 14 and 15. Why? Because these are unused states. Okay. Now we are plotting the ones and don't cares, and we are going for grouping, and this is a grouping, and the expression what you are getting is J is equal to BC. Similarly, we are going for KA, we are plotting the ones, we are grouping and we are writing the expression. Similarly for JB, we are plotting and grouping and writing the expression. Similarly for KB, we are plotting, grouping and writing the expression. Similarly for JC, we are plotting, grouping and writing the expression. After that KC, we are plotting the ones and down case, grouping and writing the expression. Finally, we are going for the output. So we are looking the column of output. We are writing the ones and down case. Then we are grouping. Then we are writing the expression. Then we are going for implementation. So we are going for implementation. Here we are using three JK flip-flops, and we have got the expressions for the input J, K, JB and JC, and we